Hi everybody. Today we are finishing off chapter 2. So we have covered sections 2.1 through 2.4. We have done two-dimensional statics problems and we've begun three-dimensional statics problems. So the lecture material for today, section 2.5, it looks really short, and it is in fact really short in terms of new material that's being presented, but there's a lot of implications to it. So we're going to work through a problem so you see exactly what this means to you. So if we take a look at the section 2.5, you look at the textbook and you see that this is it. This is the entirety of section 2.5. And all it tells you is that if you have, just like in two dimensions, if you have something that is in static equilibrium or sitting still, that the summation of forces in the x direction have to equal 0 and the summation of forces in the y direction have to equal 0. That is still true in three dimensions, except also you have to have the sum of the forces in the z direction equal to 0 as well. So instead of having two equations with a potential of two unknowns, we're going to gin that up and have three equations and three unknowns. So in other words, there's really no new information, but we have to pull it together in a more complicated way. So if we take a look at our Moodle page, I have posted the homework here. The last problem set just involves three problems, 2.102, 106, and 112. But each one of them is quite lengthy, so I'm going to work one or two problems today in class in order to get you so that you see how to set these things up. And if you have any questions, please let me know while I'm going through the material, and we'll stop and do them. So the steps that we're going to take, just like in the past, we're going to do a free body diagram. We're going to write out the problem, do a free body diagram. Then we're going to set up, instead of two equations, three equations. Summation of forces x equals 0, summation of forces y equals 0, summation of forces z equals 0. Then we're going to start filling in the blanks, and we may have to solve equations simultaneously or do substitutions or whatever algebraic techniques will get us to answer all the questions that are answered in the problem. All right, so moving over to the document camera, the first problem you're going to do is problem 102. And so I would like to do problem 2.101 as a preface to 102 to help you get started. All right, so 2.101 says we have three cables used to tether a balloon. Determine the vertical force P exerted by the balloon at A, knowing that the tension in cable AD is 481 newtons. So what we basically have, we draw our, now they draw y being up, but now they're drawing, just for sake of clarity, they're drawing that xz plane in the, this would be perpendicular to the y-axis, but it's represented this way. And we have a balloon here at point A, tethered at point A, and it has three cables holding it down, right? So I have to extend my axes so I can draw these, and C is kind of out here. Okay, so in other words, each one of these cables is tethered to the ground, so they're at the same elevation, an elevation of 0, and they all have the same y component because we're moving from point 0 up here to point A. Now all that the balloon is doing, and I could draw the balloon, but really in terms of a free body diagram, it's a helium or hot air filled balloon, so it's just pulling up, and the cables, or the tethers, are pulling down. So the first thing I need to do is to draw the directions of the cable. And since the balloon is pulling up, the cables will be pulling down, because that is what they do. Now, since this is point A, we call the point where this is anchored to the ground B, the point where this is anchored to the ground as D, and the point where this is anchored to the ground as C. B, C, D. Yep, okay, so I got all my letters there. I just want to make sure we were consecutive. Not that it really matters. But we also know then that the cable A to D right here has a magnitude. The tension AD is equal to 481 newtons. And the question is, determine the vertical force P. And we know that it's purely vertical, so it's just going to be a P sub y in the J direction. And that's what we're looking for in this problem. All right, so what we need to do, first of all, is to define each of these tensions in these cables. And so the first thing I would do, I'm going to find the dimensions, the physical dimensions of each cable. And my plan is to get a lambda along each of those cables and then multiply it by the magnitude of the tension. Okay? So let's take a look at A to B. A to B goes downward, and from point A, because my arrow points this way, from point A to point B is in the negative x direction. So let me go AB. It's not the tension, this is just the direction. AB in the x direction goes from 0 to 4.2 meters in the negative direction. So it's 4.2 meters I. From A to 0, or A to B in the y direction is a negative 5.6 meters. And in the z direction, in other words, going backward into the board or forward, it's 0. So this is the dimensions of my cable AB. I'm going to leave a little bit of space because I want to do the others kind of simultaneously. So let's do A to D, which is this one. And I think about my x direction. I'm on the same axis. So this is 0I. In the y direction, it's still minus 5.6j. But now in the k direction, I'm going backward 3.3 meters. So I'm going from this point to this point. That dimension is 3.3 meters. All right. And then the last one from A to C. If I look at my picture, I go from A to C in the x direction. I move to the right 2.4 meters, so it's positive 2.4I. Still going 5.6 meters down, so that's negative 5.6J. And in the Z direction, I'm coming out of the board, so it's positive 4.2 meters in the K direction. All right, now from each of these pieces of information, I can find the length of the cable, and after I find the length of the cable, I can find lambda, or the unit vector directed along each cable. And I know I'm going fast, so when you watch the video, you may need to slow down. But this process will work every single time when you're finding tensions in cables like this. Draw the arrow. If they're going down, draw them all down. Stick to your story. And then write the dimensions of the cable. The next thing, you want to find the length of AB. We do that using that three-dimensional version of the Pythagorean theorem. So we square each of the components, add them together, take the square root of the whole thing. And so what I have here is, I take 4.2 squared. It doesn't matter if you have negative or positive, because when you square it, it becomes positive. So if I square those two, this squared plus this squared is 49. 25, 30, yeah, that looks right. So I need to take the square root of that value. So I go second, square root, second answer, and that's 7. So the length of cable AB is 7. Let's do the same to find the length of cable AD. Square root of 0 squared plus negative 5.6 squared plus negative 3.3 squared. So 0 squared is just 0. So if I take 5.6 squared and add it to 3.3 squared, I get 42.25. take the square root of that, and that length is 6.5 meters. And last but not least, AC, the length of AC is going to be square root, this time we don't have any zeros, 2.4 squared plus negative 5.6 squared plus 4.2 squared. Take the sum and then square root. Square each of those. 2.4 squared plus 5.6 squared plus 4.2 squared equals, that is 54.76. Take the square root of that number, and it's 7.4 meters. All right. So now the next step, I want to find that unit vector in each direction. So in other words, lambda A, B. And it amounts to being the x component over the length in the x direction. And since everything's in meters, I don't have to use units. And then 5.6 over 7j plus 0 over 7, which is just 0k. Right? Now I can simplify this a little bit. I can take the 4.2 and the 5 and divide it by 7. And that's 0.6. And 5.6 divided by 7 is 0.8. So it's 0.6 I minus 0.8 j plus 0k. That is my lambda in the AB direction. Okay, do the same thing for AD. Lambda, unit vector in the AD direction, is going to be 0 I minus 5.6 over 6.5j minus 3.3 over 6.5k, and 5.6 divided by 6.5 is, this is 0 I minus 0.86j, and 3.3 divided by 6.5, it's negative 5.076, so 0.8 I jk. All right. Then finally, I'll do the same thing for AC. So lambda in the direction of AC is 2.4 over 7.4 I minus 5.6 over 7.4j plus 4.2 over 7.4k. And 2.4 divided by 7.4 is 0.32 I. Hang on, this is, I've got I wrote this down incorrectly. 3.3 divided by 6.5 equals point, and I put my point in the wrong place, minus 0.508. Sorry about that. I just realized that. Okay, so here I have 0.32 I minus, take 5.6 divided by 7.4, I get 0.76 j, and then the last term 4.2 divided by 7.4, and that is 0.57 k. All right, so now I have all of my unit vectors in each of the direction. I can now write, this is the dimensions of each cable, and then 2 is lambda along each. Okay, I'm just kind of following steps. The third step then is to write all tensions as vectors. All right, so starting with AB, the tension written as a vector of AB is the magnitude of the tension AB times lambda along AB. And I have lambda along AB right here. And I am given tension AD, so I don't know this value. So I can just write it as TAB times the vector, unit vector, 0.6I minus 0.8J. Yes,
Sorry.
sure.
Right below where you wrote the, TAB, is it TAB lambda of AB?
Right, TAB times lambda of AB. That's correct. Right. So what I'm saying here, and that's a good clarification, is that the vector tension AB is equal to the magnitude of the tension AB times the unit vector along AB. Yeah, good question. All right. TAC is equal to the magnitude of the tension TAC times lambda AC, which, once again, we don't know this, TAC, but we know that lambda AC is 0.32I minus 0.76J plus 0.57K. All right. And then the last one that we can simplify a little bit is the vector tension AD, which is equal to the magnitude of the tension AD times lambda AD. All right, we're told that the magnitude of the tension is 481 newtons, and we found that lambda AD is 0I, I'll put that in as a placeholder, minus 0.86J minus 0.508K. Right? And here, since we have some numbers, we can distribute that through. In other words, multiply 481 by each of those. So I get 0I minus, if I take 0.86 and multiply it by 481, I get negative 413.7J and then 0.508 times 481 minus 244.3K. And since this is in newtons and the unit vector is dimensionless, that entire quantity is in newtons. All right, now here comes the part that we were told about in this chapter, that the summation of forces in the x direction have to be 0. The summation of forces, that's a weird summation sign, forces in the y direction have to equal 0, and the summation of forces in the z direction have to equal 0 in order for this to remain anchored so the balloon doesn't fly away or the balloon doesn't collapse to the ground. As long as it's stable, we have to, these three conditions have to be met. So what we need to do is to go back to our vectors, tension AB, tension AC, tension AD, and also that pull, and add and break them into components. So the pull only has a J component, so I'm just going to put that here, or piece of Y, sorry. There's no X or Z because it's vertical. But now with my other vectors, AB, I'll find it on my screen, make sure you can see it. Yes, AB has a component in where did I, hang on a second. I just did something strange here. I don't think I finished that off. Here's my AB, lambda AB. Okay. Well, I just didn't put it up here. I need to just go back and just continue this. Even though I don't have values, I know that the vector tension AB is going to be the magnitude of the tension AB times lambda AB. So in other words, 0.6I, that's a negative, minus 0.8J, and then 0K.
So then that's just what we put down.
It is.
Earlier, right?
It is. I just didn't do it for AB and AD. I just did it for AB and AC. I did it for AD because I had a value, but I still need to put that. I don't know what the value is, but I do know that it's the magnitude of the tension AB.
Okay.
And you could do it below, but I was trying to stay all organized so that it would look good in your notes. So I will continue with that. All right, so now in my x direction, I need to take each of my vectors, and if they have an x component, include it here. So for TAB, I know that it's minus 0.6 times TAB magnitude. What about for AC? There it is. I did it right here. Okay. So I did write it down. I just didn't follow through with what I was doing here. So here's TAB right here. So we have 0.6 times TAB. In the y direction, we have minus 0.8 TAB. And we don't have anything in the z direction. Right? So now for AC, we have plus 0.32 TAC. And in the j direction, we have minus 0.76 TAC. And in the j direction, we have, I think I left off that decimal point again, hang on just a second, TAC 0.57. Sorry, I keep dropping a decimal point here for some reason. So this one's going to be plus 0.57 TAC. So I've got my components for AB and AC. Now I need to put in my components for AD. There's nothing here, so that equals 0. Here I have 413.7, but I've already multiplied through TAD, so I don't need that. And here I have minus 244.3. Okay, and then I have my P included. So in other words, I've broken down the components of each of the forces, and now I have 3 equations and 3 unknowns, so I can solve those. Each one of those equations, in order for static equilibrium to occur, has to equal 0. Okay, now when I look at this, you can start anywhere, but what do you see about this one? Does this look easier in the z direction? Because I can solve directly for TAC here, can't I? Do you see that? I don't have to do a substitution. I can just say 0.57 TAC, bring this over to the other side of the equation, equals 244.3 newtons. TAC equals 244.3 divided by 0.57. And so I can instantly solve without doing any fancy substitution. I can just solve that, and I get the value of TAC is equal to 428.6 newtons. Now the good news about that is if you look over here, I have TAC in this equation, so it cascades. If I take this value of TAC and put it here, I'm going to be able to solve for TAB, right? So substituting this in, this is what I do first. I'll say equilibrium equations. That would be step 4. And then 5 would be solve. All right. So after I get TAC, I can substitute it here. I get negative 0.6 TAB plus 0.32 TAC, which is 428.6 newtons, equals 0. So I can bring this over, and I get 0.32 times 428.6 equals, be positive when I bring it over to the right-hand side, TAB times 0.6, divide both sides by 0.6, and I can solve for TAB. So I take that number, multiply it by 0.32, and divide it by 0.6, and I get a value of TAB of 228.6. And the units will be newtons because I checked my dimensions throughout. So there's my first one. Here's my second one. Now I have TAB and TAC. So I can solve this for P of y, which is what I was interested in solving in the first place. So here I get Py minus 0.8 times TAB, which is 228.6. Minus 0.76 times TAC, which is 428.6. And then I failed to write if that was positive or negative. So I need to go back. If you stay organized, you never have to redo anything. TAD, TAD, right here, it's minus 413 equals 0. So that minus 413.7 equals 0. So I can just put p sub y over here, multiply each of these things. So I have 0.8 times 228.6. So this first one becomes 182.87. The second one becomes 0.76 times 428.6. And so that value is 325.74. And last, we have the 413.7. So if I add all three of those together, I get a value of P sub y of 922.3 newtons. And that is actually the answer to the question. It says, what is the vertical force pulling? It says, determine, oh, excuse me, I'd come down here, the right one. Determine the vertical force P exerted by the balloon at A. So that tells me that P exerts a vertical force of 922.3 newtons. So it pulls up with a force of 922.3 newtons, and the three tethers keep it secured to the ground so it doesn't fly away.
Can you go back to that last page of work?
Yes. No, gosh, don't be sorry. That's great. Okay.
Thank you.
Mm-hmm. Down here.
Yeah, no.
Okay. I just need a little more time.
Yeah.
Okay, that's
Sorry.
fine. No, don't be sorry. That's great. I went through it really fast because I knew we were going to run out of time, and I also knew that you would have this on video so you can go back and replay it. So I wouldn't normally, if this were a real-time class with no video support, I wouldn't have done it that fast because these problems normally take a few hours. So, yeah. So, but I will tell you that the way I've laid it out, if you stay organized like that and you keep all of your work above, you'll find that you don't have to repeat yourself over and over again. I mean, there's a lot of times when you start working problems like this that you'll find, oh, I didn't write that number down. I'm going to have to go back and I'm going to have to recalculate this, you know, and there's just room for errors. But if you go through the steps, that will happen less. And when you do them more, it will happen less as well. But so the steps are, the first thing is draw this free body diagram. The second thing is write the dimensions of each cable, and then find the length of each cable, and from those two find the lambda or the unit vector along each cable, and then write the vector tension as the magnitude of the tension times that unit vector. Okay, so those are like the first steps. Then you write your equations of equilibrium, summation forces x, summation forces y, summation forces z equals 0. You take the x components from each of the tensions or the forces in the problem, set them equal to 0, same with the y, same with the z. And then you just kind of take a breath and see if one of them is going to solve easier than the other. So if you just take a step back and don't brute force it, but come to something, you go, oh, this one's going to pop right out. And your authors do that a lot, where they let something just pop out. So if you see it, go ahead and solve it. So that's why we chose this one, because we could solve for it right away. And then even though we're looking for p sub y, we still don't have enough data to finish this equation. So then we skipped over to here, because we had this, we plugged it in, and we solved for that, and then we finally came back and got the answer that we wanted. But the setup is the whole thing. The other thing is when you take a quiz or when you do the exams, if you show me all of your work, I can give you a boatload of partial credit, you know, because this is the kind of thing where a lot of people will make an arithmetic or an algebra mistake, and if that happens, I don't want to nail you to the wall for something that's minor. So if you show me your work, I can give you more credit that way.
And then For the quiz that is due on the 13th,
Yes.
do you need to turn our work in through Moodle?
Absolutely. So yeah, when you take the quiz, and I'll leave it open over the weekend too, so it'll be open till Sunday night. When you go to the quiz, oops, you probably want to see that. Here we go. All right, so it gives you some directions here. Basically, it's worth 100 points. There's going to be 5 parts on the quiz that are each worth 20. And you'll do the quiz, but you'll have a piece of paper in front of you and you'll work it out. So then within that 1 hour time frame, the quiz will shut down. You'll have your answers on the quiz, but some of them are just like email. You'll just write the word email. So you'll take your piece of paper that you did your work on and then just email that piece of paper to me. And then but do it within that hour window, in other words. So, because that's part of the timing. And so then when you do that, you can see I'm in progress because I took the quiz to make sure it wasn't weird. But you'll have a button down here that says start, and then it will warn you. It will say once you open this up, you only have an hour to do it. So, and if you're not done, don't worry about it. I mean, just do as much as you can, and then that's what you'll be graded on. And I'll give you a critique. I mean, it's not just a grade. What I'm really trying to do is to get you ready for the exams. So I want you to see what that's going to look like. So, sound like a deal? All right. Well, thanks everybody. Thank you for coming today. I'll post this lecture, and we should be good to go. And don't hesitate to get a hold of me if you need help. I will be on campus all day tomorrow. I'm not going to be here this afternoon. I have to go to Billings and do something with my mom, and so I will be back tomorrow morning. And so anything you need, send me an email or stop by, and we'll get her done. All right. Have a great day.